Hello and welcome to this technology demonstration of some of the technical features of the Evolving Networks Intelligent Network Fabric. I'm Nick Elliott, I'm CTO and co-founder of UK SD-WAN vendor and network managed services provider Evolving Networks.
Yeah, I'll get straight into it then. Evolving Networks, the UK's only soft SD-WAN vendor. Most of the SD-WAN technology vendors are from North America, but we've been writing software since 2008 to make connectivity better and delivering that as a service. As Ian just said there, one of the key differences for us is that we are providing that network underlay as well, and we're doing that across our agreements with multiple ISPs, so that there is that end-to-end managed service. It's the DIY approach if you were to do it, but fully managed by us, and with the experience we've got now of over 13 years. Of putting those components together and managing the entire supply chain, but with some differences in the way that we do the software as well. We like to say that we transcend the traditional ISP. We're elevating ourselves above all of those telcos, and we're picking the best bits of them. We're taking circuits dependent on the locations of the individual end users and the offices, or the apps and services in a core network. We're choosing the best ways of connecting to those. We're looking at the level of risk that any customer wants to take, risk, bandwidth, access, security, and piecing together a fairly complicated looking network underneath, but putting our network fabric on the top to make that really, really simple and benefit from all of those multiples of different carriers and different types of circuit. So our intelligent network fabric is what we call our kind of suite of network technology. And again, there are differences between the way that we deliver our network fabric compared to other SD-WAN vendors. And that comes down from some decisions we made very early on as to how to build it. But it does allow us to deliver multiple different topologies, layer 2, layer 3, private, public, on any number of sites in any combination of locations. And what we do is we create these customized network instances for each customer. What this presentation doesn't particularly go into is the kind of engagement methodology that we employ through our partners, where we go through a series of collaborative workshops. We're auditing the network, we're finding out where users are and where applications are, and then mapping that onto the current and future needs for that business. But the point is, we do go through that process, and at the end of it, we create something that's unique for every customer. So this isn't just the same as a telco that's partnered with an SD-WAN vendor, and they install that in their core network, and then that's it. You can connect to that. If you want a bit of it, there it is. What we do is we create things that are very specific to the needs of each individual customer. And we do that by connecting one of our appliances, an EVX, onto the end of any site, or into a data center or in a cloud provider. So there are physical appliances and there are virtual ones as well. As I've said before, we can reach any of these locations. Where this is about connectivity now that, certainly as a result of the last 2 years, has spread out quite dramatically. Most businesses were on some kind of journey of digitalization, of moving things out of single points of failure, taking things out of head offices, moving them into data center, moving them into cloud locations, or a combination of those. But likewise, on the user side now, the WAN footprint has changed quite dramatically. There's a lot more home workers, a lot more flexible workers, road warriors. There's a lot of places to connect. It used to be that we would provide people with a connection to the internet, and that's a journey that most businesses have gone through, of maybe initially connecting their sites together before they had an internet connection, then they have an internet connection, and such was the growth of MPLS for site-to-site connectivity. But then as broadband became cheaper, and then lease lines became cheaper, internet internet transit became cheaper, and so that push and pull of private networks versus public networks came in. What we're saying now is, it doesn't matter where you want to connect to. We'll connect to wherever you need to. We'll design that network for you, dependent on where your users are, dependent on where your applications are. And also importantly, we'll start you on a journey of continuous network transformation. We're no longer in a situation now where businesses buy a network, buy a wide area network, and then stick to it for the next 3 years and it doesn't change. It has to change. This is like painting the fourth bridge. It'll never be complete. And so what our software technology allows us to do, and we can be more flexible on the contract side as well, is allow a customer to start on that journey, maybe fix some pain points, and then start changing their network fairly constantly in line with the business transformation that they need to make. And these networks can look quite complicated. This actually, in the scheme of things, is quite a simple one. This is a 3 data center setup, 3 identical connections to the internet, to carriers, and to Azure. But if you imagine that this could have multiple cloud providers on it, it could have 2 data centers, 4 data centers. This could be across regional, global networks. You could have POPs in different countries. You could have different racks of servers in different data centers you've got to access. The point is, we go through that process of learning what it is we need and where we need it. And we put the right contract terms in place for those elements, depending on how long we think the customer is going to need them as well. So there's one of our EVXs. We've got rack mount devices. We've also got, there's another picture later on, you'll see the smaller footprint device that can go in branches and also in home workers as well. But I'll revisit this again a bit later on. We're different from the other SD-WAN vendors. This is about packet aggregation. This is about taking all of the available bandwidth and using it. This isn't dynamic path selection. It's not wasting bandwidth. But because of those decisions we've made, we get to be able to do a number of other things, like create complex layer 2 networks with VLANs, for example. We fundamentally take a decentralized approach wherever we possibly can. There isn't a central SD-WAN controller that is constantly talking to each of the nodes out there, that is a dependency for them to be able to make changes, or for them to be able to react to certain situations, or even for them to be able to boot up and be able to function on a site. And because of the way we architect everything, we wrap it all up in big SLAs. So we're always talking about 100%, but then there's a sliding scale up to 10 times your money back for any downtime in any situation, and that's linked to just how resilient you make that connection in terms of the number of circuits, the number of appliances, the number of data centers, etc., etc. So the aggregation technology, this isn't failover, this isn't policy-based routing. This is taking the bandwidth of any individual link and adding them together. And because we do that, we can use all of the bandwidth for any single stream of data. So this isn't about saying you've only got the bandwidth of one link for one particular service or one session with one user. We encrypt everything end to end. And because we're dealing at the packet level, it means we can get to do some other clever things later as well. What it does give us is the ability to transcend above that ISP layer, as I said earlier. And so here's a simple example here of where we might put 4 circuits in with 4 completely different carriers. That means you can lose an entire circuit or an entire network. These days you still got line faults, and our mantra is everything will go down at some point. That's why we over-engineer these connections. But actually, some of the issues that people see more often these days aren't specifically to do with that last mile connection as it comes in. Obviously, you're protected from those failures as well, but the ISPs themselves, the networks themselves, we've seen lots of examples of this just this year. Of big network issues that take down an ISP for hours or better part of a day at a time. What our technology and our approach allows us to do is to avoid those problems entirely. And again, you've got to look at this scenario here. This is just one site, but if you've got 50 sites, you've got 100 sites. then again, we will balance the ISP mix around those so that no one site is dependent on any one singular ISP. So you've got an independence there above that ISP layer. Everything else we do is done at that network fabric. And that also allows us to migrate circuits around as necessary if they're misbehaving. If we've got broadband circuits, even lease line circuits, depending on the type of issue we have, where we're seeing recurrent problems that we're having to work around, months and months on end, then we will actively move those circuits. And that can be completely transparent for the end users and for the customer, because we're dealing at that network fabric layer. So the things that we change underneath don't have to change what's above that network fabric layer. As I said, because we are doing things at the packet level and not the session level, then we get to employ some really good bi-directional quality of service. This isn't rudimentary throttling. This isn't about saying that, that bulk upload only gets 20% no matter what. It's about saying that any service, any application, any user can achieve the full bandwidth of the entire connection as long as there's not a higher priority bit of traffic that needs to use it. So as soon as someone's making a VoIP call, as soon as there's some form of virtual desktop infrastructure, anything that's time sensitive, those packets will get priority over the others. But it does mean that the rest of the bandwidth is then available for any else of those other services. So it's a much more efficient use of bandwidth than just merely sending some packets to the left and some packets to the right. And I mentioned that DIY approach. We've taken a blank sheet of paper here and said, how would we manage the best network we possibly could if we were doing it for a customer? If you were to do it yourself, you would have to go and get an SD-WAN provider. You'd have to get involved with more than one ISP, more than one data center. You'd have to source the hardware. You'd have to learn how to provision. You'd have to provision the modems and keep an eye on the firmware of that as well. You'd have to monitor it all, and you'd have to be responsible for pressing go on a major network change and hope that it all works. That's what we do. We do the whole lot altogether, and we've been doing that for over a decade. So let's get into the demonstration. So what we're going to cover here is our kind of full technology stack. We're going to do some demonstrations of link failure and data center failure, and also show you how the QoS works. We're going to give you an insight into how we design SD-WAN backbones for our customers, and the kind of complex topologies and network presentation that we can do, which we think elevates us above the competition as well. As I mentioned before, we're different in a number of ways. One of the key ways we're different is that we're not basing all of this on IPsec tunnels. This is a custom UDP encapsulation that we've developed, and we're tunneling at a layer that allows us to do an awful lot more on the topology side, which you'll see. As I said before, we're not doing policy-based routing. This isn't dynamic path selection. This is aggregation by packet. Again, the element that's not so much about the tech, but about the mindset, is that we're managing that end-to-end supply chain as well. And so that means no wasted bandwidth, far more complex topologies. We can scale up without running into issues of numbers of tunnels and things like that. We can match the kind of global hubs that a customer might already have for their application hosting and for where their users are, and build something that's customized to that, as opposed to saying, look, here are our POPs. This is, you connect to your nearest one and hope for the best. We build out the network as necessary for whatever is needed for that particular customer in that particular scenario. So our network software architecture, what we call our intelligent network fabric. This is a depiction here, not just of the kind of three major sections that you can break it down into, but you're kind of almost showing here a left to right view of the kind of the direction that packets would flow and what happens in that order. So on the right hand side, you've got what we call our link enhancement technologies. This is everything from encryption to forward error correction. UDP masking is a technology we use if we need to avoid someone's UDP throttling, which we have seen. We saw that at the back end of last year. OpenReach in a number of exchanges started throttling UDP traffic, one assumes because of the rise in home worker use as a result of sending people home. So we've got a number of tunneling mechanisms we can use to avoid some of that throttling. Then in the middle, we've got our multipath packet vector engine, which is that collection of technologies, everything from the aggregation, the reordering to the QoS, and that vector decision engine as well, dependent on the network presentation. This isn't just about simple internet connections. It's not just about simple layer 3 networks, but any combination of VLANs, layer 2, layer 3, private and public. And so again, there are vectoring decisions there to be made dependent on how resilient the network is that we built for the customer, whether we need to put quality of service on, whether we need to do any reordering, etc. And so you can see that that's the kind of general overview of what we've made. The larger technology stack I've represented here. Not expecting everyone to read every word on here. We've got our collection of technologies specifically to that we've applied, but then also a bit of an insight into the level of just standard networking that we can deploy as necessary, whether that's on the QoS side or on the routing side, or if we want to connect up to other people's services with different tunnels or VXLAN or things like that. We've got the entire network stack at our disposal, and what our development path is about automating more and more of the provision of any of the elements of these. But what we can do is we can run on a number of different bits of hardware. We can virtualize virtually anywhere, and we can deploy on top of our network fabric all of the kind of standard networking technologies that you're familiar with. So this demonstration is going to show you how we aggregate bandwidth. It's going to talk about the overheads involved and compare them to the overheads on standard connectivity. What you'll see is the trace route out of the network and how that might change depending on various types of failure. The fact that we wrap everything up into a single IP range for this demonstration, but as I said before, it could be a layer 2 connection, it could be a combination of VLANs. For this demonstration, this is a nice straightforward to the internet mock-up, just so you can actually see things as they happen. I'm going to show you link failure, I'm going to show you data center failure as well, and the convergence times. So in traditional networking, you're all familiar with connecting to the internet. What we've got in this scenario is a client machine. It's connected to a firewall, very, very simple LAN setup connected to a 200 meg lease line with Virgin Media Business. And we're going to test throughput to a server on the internet. Now, this isn't a demonstration of our portal. This is about seeing things in as granular a way as possible. So this is a technical view that you'll see now on this next slide. So because we want to show things that are sub-second in nature, that's why we've gone for this type of view. So apologies for the less technical amongst you, but what you're seeing here, top right quarter of the screen is a live trace route. The left-hand side of the screen is a live show of the throughput going through the connection. And then the bottom right is a refreshing every 10-second web page, essentially. It's actually just loading a JSON file from ifconfig.co. This is the equivalent of what is my IP. And so what you can see here is that it's loading a Virgin Media IP address on the end here. I'm on a 192.168 address on my client. So this is all of this is from the perspective of the client machine. And you can see on the trace route here, 21.1 is my firewall. And then I'm straight out through the Virgin Media network out to Google DNS. So kicking off the download on this 200 meg connection, and we see on the graph on the left here, settling there at 191 meg on that Virgin Media IP. But importantly, look at that top right over here. We're already over 120 milliseconds to saturate that connection. So the latency and the jitter have increased in order to get that 191 meg out of this 200 meg connection. So there's none of our technology in play here. This is a machine connected to a basic firewall connected directly up to that 200 meg lease line. And as you see at the end there, the latency steps right back down again, back to normal levels. So there's that traditional networking, and I like to compare to this in order to show people that you don't get all the bang for your buck even with a normal connection. There's an overhead there of around 4.5% to give us 191 meg. That's fairly normal. It does vary a little bit from carrier to carrier. It varies a bit more depending on whether you're putting a broadband link in or an FTTP service or an Ethernet service. But there are overheads in getting you that bandwidth. But also, there are Ethernet overheads, there are TCP overheads and things there as well. So we've got 191 meg out of that 200. But importantly, in order to get that, there was a big increase of latency to over 120 milliseconds. So now let's connect up an EVX. So yeah, here's the other example here. The box on the left is our smaller footprint hardware. We've also got other models that I haven't got photographs on here. Some of them are even smaller. And we've got tiny devices now that people can take into the home. That if we don't want the full stack of quads and aggregation, but we still need access, we still need security, we still need visibility, then there are even tinier footprints of devices now, pocket-sized USB devices that people can plug into their existing connectivity. But this device on the left here allows us to have a single footprint device that can also have, you can just about see the SIM slot on the side. This can have 4G in it. It can have Wi-Fi aerials sticking out the back, and we can also plug SFP modules in the front as well, depending on if we want to put in VDSL modems or other technology for a single footprint device that's great for retail settings and for home workers as well. It's a fanless device. So if we plug in our EVX now and we show you what happens to exactly that same connection as it runs through our network, as you can see on the diagram here, we're putting our EVX in, but we're also running through on our data centers before we get to the internet. So we're applying that network software overlay to this single 200 meg connection. So just for ease, we're through a different firewall now. You can see that we're connected to a 10.38 address on the client. 30.1 is our default gateway, which is our firewall in our lab. And you can see here we're then coming out of our network through one of our partners at RedStation out to the internet, out to Google. Likewise, you can see from the What Is My IP service here, this is an evolving networks IP. This is on our AS number. We can present other people's IPs as necessary, with obviously a bit of ripe work. And so we can present customer IPs, we can present your IPs if you have them. But the point is, this IP address, this /30 range, has been applied to the network fabric. It's not tied to the individual circuits. So if we kick off the download on here, we'll see we're stabilizing there at 177 megabits per second. And that's running out through that Virgin Media lease line, but also through our network. So yes, there's an overhead involved here, but importantly, look how stable the latency is in this scenario. Yeah, so we are running our throughput over there. This is to the internet, but the latency and jitter is absolutely bang on. So once we connected up the EVX, we were given 191 meg. That was our usable throughput. And it's worth showing you here how things break down. So we've got an encapsulation overhead of around 4%, and then a quasi overhead of 3%, which is variable depending on the type of connectivity that we connect to. So we can sometimes even get lower, as low as 2 or 1%, depending on how stable the circuits are. Sometimes we adjust that a bit higher if we're dealing with, say, some lower bandwidth ADSLs or FTTCs. But what that's giving us here is that 177 meg throughput over that connection. But importantly, latency and jitter are unchanged. And this is a standard quals profile that we've applied here. And I'll show you the buckets that uses for prioritization later. But what it's trying to do there is make sure that time-sensitive traffic, including ICMP, is getting through. But likewise, things like DNS requests and other things that make a web page faster are prioritized, so someone can do a big download, but people can also browse the internet as well. Which, let's face it, an awful lot of things now, web applications, and not notice a slowdown. So where do we go from here? Well, let's add another link in. So we've got a TalkTalk Business 200 meg service now. And so what we're going to do is plug that into the same EVX and see how the aggregation works. As you can see, the IP address hasn't changed. We're still on there. The trace route doesn't look any different. But now, as we kick off that download, we're up at 354 meg. So that is twice that 177 meg. There's no additional overhead from the aggregation itself. The overheads that we see are because of the quality of service queuing and because of the encryption encapsulation that we do to actually tunnel in the first place. Again, stable latency there, stable jitter throughout that download. So we take those two 191 meg circuits, that gives us usable throughput of 382, exactly the same overheads, which gives us that 354 meg connection. No increase in latency or jitter. So let's see what happens now when we start doing some failure testing. Now, I do like to show people what happens when you kill a standard connection. Everyone's familiar with it. Here's our 191 meg throughput. Again, we're back on the Virgin Media Link on its own, 130 odd milliseconds of latency, but we just pull the plug. Everything's plummeted down to zero. You know, you can start seeing loss now registered on this trace route. And this is that moment where you start to go, oh, have I lost my connection? Will that web page load? You know, click F5 for refresh. If you're on a call, everyone's frozen by this point. You're wondering whether it's just going to come back or not. This amount of time for this outage we're simulating here, literally just by pulling a cable out and plugging it back in again, is a very familiar sight to a lot of people, certainly after they've been sent to work from home. This is the kind of time frame. You can see there the refresh of that page has kicked in now. It can't load it anymore. This is the kind of outage that is commonplace and the type that will have you reaching for your mobile phone to maybe tether your laptop to on 4G to try and regain a connection. And you can see there, as soon as the connection comes back, everything just resumes again. But let's talk about the convergence time for us. So when we're aggregating circuits, we're down in that sub-third of a second territory for circuit failures. It's barely noticeable, if at all. The kind of normal everyday slight blip you might see or hear on a VoIP call or on a video call would get hidden by this type of change. So again, we're back on the EVX now. We're connected to both of those services at the same time. 354 meg, solid download, as you can see. We're on our Evolving Networks IP range. But if we then unplug that Virgin link and see what happens, there we go. We step down to 177 meg. Notice, no change in latency, no change in IP. There's a little adjustment here while TCP, works itself out to work out how much throughput it's now got available to it. But we've just stepped down to the amount of good bandwidth that is left in this connection. And, we've deliberately done this as a simple one. This is just 200 megs. Once that circuit comes live again, you see that bandwidth just gets seamlessly added again and available. No change in latency, no loss, no change in the IP because the IP is tied to the overall connection. Just for completeness, we've now just unplugged the TalkTalk line in this scenario. So again, very, very similar things happen there. Slight adjustment, tiny amount of packet loss for that less than a third of a second while it adjusts. And then as soon as you plug back in again, everything goes back up to the full bandwidth. It's completely seamless, and the latency is stable for the entire time. So a bit of a chat about exactly how we architect our networks, and that's important for the next demonstration that we do. So what we're depicting here is a smallish network, 6 sites, but connected to 2 different data centers. So whatever network we provide for a large number of sites, we spread those sites over an SD-WAN backbone over multiple data centers. we're not doing things in an active passive way where that secondary data center is only used if there's a failure in the primary. We're spreading the sites over, and we're making sure that we never run any of that core infrastructure past 50% in this scenario. We could have 3 data centers and spread things into thirds and things like that. There are other ways of doing it, but the point is, if we have a failure, we want those services to be picked up straight away by the other parts of that backbone. And importantly, what you can see here is every site is connected to both at the same time. So there is a primary vector and a secondary one, but there's no reconfiguration that's necessary at all. There's no central controller that needs to tell those sites, oh, that data center or that core bit of infrastructure has failed. You now need to go and change your configuration. You now need to start sending data up there. Each of these sites will make that decision independently because we've already instantiated the config for this setup. So if that data center on the left were to fail, none of the sites on none of the green sites would be affected at all because they're still connected to a data center that's live. But all of the white sites on the left, they would all start routing or vectoring, if this is layer 2 traffic, over to that other data center without any intervention whatsoever. And that spine and leaf topology is how we build out our networks for the maximum amount of resilience at the core level as well as at the edge, but also to make sure that we're not hoping that a device can work. We're using every device in the network to make sure that we know it's there when we need it, which is the same approach as we're taking with the bandwidth aggregation themselves. This isn't about just having a backup circuit and hoping for the best that it works when you need it. It's about using all of the available bandwidth all of the time. So let's have a look at data center failure. Now, we've got a couple of different convergence times here, not least of which because when you're dealing with the internet, you've got BGP timers and things like that to kick in data centers. But we're basically talking if there's a failure of a big core bit of infrastructure, then site-to-site traffic, SD-WAN traffic, would kick back in again through secondary routes within about 15 seconds. Internet upstream type stuff, and again it can vary a bit if you're dealing with cloud providers as well, is around that 30-second mark. So again, it can depend on the data center provider and the upstream technologies and services there, and it can also depend on the number of hops as well, if you're going to have some form of propagation that needs to go up the chain. So what we'll show you here is the aggregated connection again. So you can see the 354 meg solid coming out of this particular data center in the trace route. But importantly, what we're going to do now is effectively turn off that data center. What we've done here is we've turned off one of our network fabric routers. Okay, and what you're going to see is you're going to see the trace route change. Now, if we had more than one site connected up, you'd see that by about now that site-to-site traffic would have already kicked back in. But as I say, this is an internet-facing test. We're doing throughput to a server on the internet somewhere. It takes about 30 seconds. But what you're going to see in the top right, there it goes, is that trace route change. And then immediately, the throughput then carries on. But note, the overall IP address of this connection hasn't changed. We just refreshed that MTR to clean it up a bit. You can see we're still getting out to Google DNS. We're still on the same IPs, but we are now taking a different route out. But I think it's important to talk about recovery as well, because when we're moving stuff around between things that aren't live, or because something's failed, then the convergence times do need to be in the seconds. But actually, if you're moving infrastructure around for things that are already live and have already got their routes set up, it can be very, very quick. So seeing how things would move back. I don't like using the term fail back in this scenario. You're moving the things that should be on their primary core router back over again. You'll see that it's seamless. It's instantaneous. So again, if you look at the trace route, we're on that second data center now. It's not the same as it was. We've got our 354 meg of throughput, but then what we're going to do is turn back on again that network fabric router in the SD-WAN backbone. It then boots up, goes through some health checks, make sure that it can actually operate in the way that it needs to, and as long as everything agrees with that, off it goes. There we go. It takes back over again. So you can see the tracer it's updating there. We'll tidy that up just by running the MTR again. No change in the IP range on this connection. And yeah, look at the graph on the left. Barely a little blip while it reconverged between the two. So what can we do with that? We can build complex connections where the overlay has got high bandwidth in it. We can make sure there are no single points of failure right from the edge where the EVXs are through to the data centers, through to the connections to the internet, the connections to the cloud, the connections to other people's networks if necessary. But all of that is wrapped up into one transparent connection from firewall or switch through to whatever that service is that you're trying to get to. In this case here, high bandwidth, up to 2.6 gig here on this connection if the 5G and the FTTP behave themselves. But we can lose an entire appliance, we can lose 3 entire networks, 3 links, we can lose a data center as well, and we can still have our connection. And so we go through this process of understanding what should be needed at each individual site as part of a network. It's not one size fits all. It's about what's available, but it's about what's needed as well. And we go through what we call a virtual topography with any new customer in order to kind of throw out there, where are your users, where are your applications, what do you need from a security standpoint? And then we start drawing the lines up to show where those traffic flows are and start getting understanding of where the resilience is needed, where the bandwidth is needed, and what directions those flows go in. So a reminder of our network technology stack. We are employing above the network fabric some very standard techniques for doing networking. As I say, most SD-WAN providers, it's a subset of these. So we do get to do some cleverer things with more complex topologies. And on the QoS side of things, we've got a number. I think I said I would show you the QoS buckets. That's on the next slide. Here's just an example of all the different things that we can use to create a QoS profile. And we've now got our signatures for various applications. We're growing that all the time. We've got our standard profiles that deal with 80% of situations. But we can also work with a customer to nail an individual application flow as necessary to work out what it is and where it needs to go in the priority list. And so here's a very, very standard QoS profile for us. We can create additional classes of traffic as necessary, but something in this kind of 4 bucket range tends to work, because you want to make sure that your keyboard strokes and your mouse movements of your RDP sessions are given higher priority than the email that's leaving your outbox. So again, remember, this is wrapped up in the entire aggregated connection. This isn't just about sending traffic down one particular link. It's about using all of it. But the point is, any of those elements of traffic at the bottom level there of what's classed as low priority could stretch up and use all of the available bandwidth if it's there to be used, and they will just get flexed downwards again if the other traffic appears. And on that networking side, what we've created above this network fabric is the ability to create whatever type of topology you want. This is a complex one. This one here is an example of what you could have on 4 ports presented on an EVX on site to a customer. And it doesn't have to be, they could have 100 sites, and this could only be what is represented on 3 of them, or 10 of them, or 50 of them. And there could be other topologies that exist for other connections on that network. So it's not just about creating one virtual WAN and that's it. So in this instance here, we've got public routed to the internet on ETH0, a nice simple untagged VLAN port. You would configure a static IP on your firewall and connect up to it, no bother at all. Then Ethernet 1 has been separated into 2 sub-interfaces, 100 and 200, which themselves go to 2 different private routed subnets. So we've got 2 layer 3 networks here that could connect up to potentially 2 different data centers or 2 different cloud providers, or just 2 other collections of sites that had the other ends of those WANs on. And then the fourth port here has been set up in a kind of raw layer 2 fashion, trunking whatever VLANs a customer wants to tag and plug into them, and have them stretch and spit out the other end to wherever else we wanted these to trunk to. And again, we can lock these down. You could have multiple trunk ports. You could have certain VLANs coming through one set of sites, and then another port with another set trunking through to other sites. Without them clashing, they would all be separate in different VRFs. So the level of complexity that we can employ at that top level is unsurpassed compared to other SD-WAN vendors. We can create complex networks above that network presentation layer, regardless of the number and type of links that are underneath. So a reminder of our software architecture. We call it our intelligent network fabric. We break it into these three: network presentation, the complex topologies, the multipath packet vectoring, how we are making those vectoring decisions, classification, reordering, and aggregation. And then on the link enhancement side, maybe we want to improve the connection of a 4 or 5G service by employing something like forward error correction. But also here's where things like the encryption technology occurs as well. This happens at the edge. It happens in the SD-WAN backbone before we're then handing off to cloud providers, internet, data centers, or wherever else. And that's where we come to an end. And hopefully you've got a load of questions.